Over the last few years, I've noticed a lot of buzz around AI, specifically as a term applied to microprocessors and microcontrollers. I've seen more than a handful of boards being labeled as an AI development board, and it's an ARM Cortex-M4 and a handful of sensors. When you dig into the datasheet, you find that the ARM Cortex-M4 is no different than any other Cortex-M4 out there, and certainly a handful of sensors doesn't magically give something AI abilities. So what makes something a true AI hardware accelerator? Luckily for us, we've got Tumas, a senior hardware engineer at ARM, to help answer that question.
Thank you, Sean. Let's start with first looking at what defines TinyML and TinyML applications, and then we'll take a look at what hardware there is available and suitable for such workloads. The most common definition used for TinyML is on-device machine learning applications in the single milliwatt and below. These are normally microcontroller systems powered by small batteries and possibly by making use of energy harvesting. The most common applications for TinyML can be roughly classified into three main domains, or the three Vs. As shown here in order of increasing compute, these are vibration, voice, and vision. Vibration includes systems that not only control a motor, but also do predictive maintenance localized to the specific motor. Voice includes systems with one or several microphones to be used for voice keyword detection and speech recognition. Vision include industrial systems recognizing objects to be able to sort items and spot defects, or systems detecting human presence, or systems identifying faces to unlock devices. All of these use cases have different workload performance requirements and demand scalable solutions. To date, ARM's partners have shipped over 52 billion microcontroller units, and millions of developers are comfortable designing with Cortex-M devices. We are now building upon the M-profile architecture and making it easier for endpoint devices to sense and interpret the world around it. This requires signal processing to make the input usable, and machine learning processing to provide more useful intelligence and action, making compute at the far edge a reality. Computing at the edge is also becoming more important for Internet of Things implementations to address latency, autonomy, network bandwidth, and not at least privacy and security issues that are inherent in many Internet of Things applications today. On the vertical axis, you can see a general mapping of traditional compute performance, while on the horizontal axis, you can see the relative level of signal processing and machine learning performance. You'll notice today we do have signal processing capability in our Cortex-M4, M33, M35P, and M7 cores, easily available through the open source CMSIS libraries. The light blue box in the center of the slide represents new performance points and new application areas that can be served by the new Cortex-M55 processor, the first M-class processor to support the Helium vector extension, significantly increasing the machine learning and DSP processing capabilities. Finally, the most ML performance system can be achieved by pairing up the Cortex-M processor with the new EthosU micro NPU. Here, there are many configurations available, all giving substantial increases in machine learning performance and energy efficiency. We will now take a more detailed look at these two new ML products from ARM, the Cortex-M55 and the EthosU55. Let's begin with the Cortex-M55. The Cortex-M55 is the most AI-capable Cortex-M CPU, combining Cortex-M ease of use with our Helium technology for enhanced DSP and machine learning performance. Its highly optimized vector processing capability brings up to 5 times the DSP performance, and its 8-bit dot product instructions yields up to 15 times machine learning performance. These capabilities make it versatile to excel both on classical machine learning and on neural network-based machine learning algorithms. Its memory interfaces have been optimized to swiftly fetch data and machine learning model parameters, as machine learning is as much a data access challenge as a compute challenge. Additionally, security cannot be compromised in Internet of Things, and the Cortex-M55 comes with a full trust zone support. Furthermore, the M55 is highly configurable such that area and power can be optimized for a given system by only including the features and components that are needed. This includes configurability of tightly coupled memories, caches, floating point support, debug, and more. Let's now have a deeper look at the new Ethos U55. The Ethos U55 is the first micro-MPU designed for use together with Cortex-M CPUs. It is targeting embedded type systems with on-chip SRAM and typically a low bandwidth non-volatile memory such as a flash. It is a dedicated accelerator for neural network workloads, fully offloading the CPU for all of the most popular neural networks, convolutional as well as recurrent. It includes support for compressed weights, allowing for the neural networks to use less storage, as well as lowering the required system bandwidth. The Ethos U55 can be configured in 4 sizes, ranging from 32 to 256 multiply accumulate per cycle. The U55 can be paired with a range of Cortex-M processors, but the ideal ML solution is achieved when it's paired with the new Cortex-M55 processor, as machine learning applications generally consist of a mix of neural network processing and more traditional signal processing workloads. Just announced is also the second generation micro-MPU called Ethos U65. The Ethos U65 extends the configurability up to 512 multiply accumulate per cycle and also extends the support to systems with DRAM. The U65 still relies on an M-class processor to control it, but the M-class system as a whole can be integrated into an A-class system, creating a machine learning subsystem to be used, for example, as always-on type functionality. Let's now take a look at how to map neural network workloads onto the Ethos U micro-MPU. As important as the hardware is, machine learning applications rely on tooling and software frameworks. A popular framework for TinyML is TensorFlow Lite, which is one of the frameworks initially targeted. The workflow starts on an offline host to the left in the figure. The neural network is processed in the TensorFlow framework to generate a TensorFlow TF-Lite file. If the target system contains an Ethos U accelerator, the TF-Lite file is passed through an offline compiler called Vela. This will replace all operators supported by Ethos U with a compiled graph and create a new TensorFlow Lite file. This TensorFlow Lite file can now be deployed on the target device to the right. All, or the majority of the network, will now run on the Ethos U. Anything not supported by Ethos U is run on the Cortex-M using CMSIS-NN optimized library calls if that is available. As can be noticed, deploying solution is transparent to what the underlying hardware is, as long as the TensorFlow Lite file has been compiled before deploying it. Let's now have a closer look at this Vela neural network compiler. Vela is an open source compiler for the Ethos U micro-MPU series. It reads a TensorFlow Lite file and outputs a new optimized TensorFlow Lite file for Ethos U. In this process, it identifies all subgraphs of the neural network which map to the Ethos U, and for these subgraphs it generates a compiled command sequence for the micro-MPU, including compression of the weights. This process not only significantly optimizes the speed of the neural network, it also reduces the model size and the amount of SRAM needed for the processing. This can be very significant and will enable use cases not previously possible on constrained embedded systems. Let's have a closer look at an example of what kind of performance optimizations that are possible. In this slide, we are taking a look at the pure neural network workload. We will look at a full application in the next slide. Specifically, we are here looking at WAV2Letter, a network used for speech recognition. To the left, we can see a 3.5 times improvement of just using CMSIS-NN over unoptimized TF-Lite reference kernels. This is using an M4 processor. If using the Helium-enabled M55, you get an additional 11 times improvement. Finally, coupling the M55 with the Ethos U55 micro NPU, you get an additional 25 times improvement. In total, this is almost 1,000 times faster than unoptimized M4 code. However, just focusing on the neural network is not giving the full view of an ML application, although it does give a good indication of how efficient the Ethos U micro NPU is on such workloads. Let's take a look at a full voice assistant use case, including advanced pre-processing of the audio, such as beamforming and echo cancellation, and conversion to MFCC coefficients. We also now use the more performant M7 with CMSIS NN optimization as the baseline. On this level, we see the M55 bringing a factor of 6 speed up over the M7, and paired with Ethos U, it's a factor of 50. However, also note the significant energy savings. Up to 25 times less energy is consumed when using M55 and U55 together. Finally, let's summarize with a rough guidance of what kind of hardware is suitable for the different machine learning applications. Starting at the left, existing Cortex-M systems can already today enable vibration-type applications and simple voice-type applications, such as keyword detection. By making use of the Helium vector extension set in the Cortex-M55, more advanced voice-type applications are possible, as well as simple vision-type applications, such as anomaly and object detection. When paired with the Ethos U55 micro NPU, full voice-type applications like speech recognition become possible, as well as more advanced vision-type applications, such as gesture detection. To reach the highest performance points, including advanced vision-type applications, you typically need an A-class system paired up with a second-generation micro-NPU, Ethos U65, or the client Ethos N series NPU. It shall be noted that the amount of compute required for a given application depends heavily on the target accuracy of the application. For example, in voice-type applications, the amount of compute will depend on the number of microphones used, the bit accuracy of the audio, and what type of accuracy the application is targeting. Even a small percentage of accuracy can come with a magnitude of added computational cost. It should also again be emphasized that selecting a hardware more dedicated to machine learning, such as a system with a Cortex-M55 or Ethos U55, also come with a significantly improved energy efficiency, as shown in previous slides. So, the best hardware to select for your system will depend not only on the type of application, but ultimately also depend on the quality, accuracy, and power targets. So, by providing the broadest range of ML-optimized processing solutions, ARM is set to enable the widest range of applications.